Let's start. I think you guys can see my screen, right?
Yep.
Cool. Let me try to bring in the slides too. So yeah, let's start quickly. Uh, we are going through the part A, and I will try to finish part B as well. Uh, now, uh, let's start from the top. Here we talk about self-supervised learning and a pretext task. With this lecture was taken by Ishan of Facebook, and uh, he starts with the success stories of supervision and the pre-training, uh, what it is, how we look at it. And quickly, I will like to go in the initial uh, annotation. We all know the magnitude of the data sets, how and why they are so wide, and in the real world, uh, uh, it's time consuming, expensive, and many folks know about Amazon Turk, and yeah, and so on. And because of this research into uh, self supervision started, and these approaches where the label is the property of the data sample, and because of the task in real world, like in semantic segmentation and video classification and other uh, downstream tasks, we need a lot of uh, object level category, the set of uh, that semantic differentiation with respect to uh, if I take a real life example, like in self-driving, yeah. So uh, uh, that's the basic example in which if we consider Tesla or Waymo, for example, uh, they have to get the data to try on the uh, navigation and other downstream tasks. Uh, for the training purposes, we need some kind of uh, representation learning where uh, the large quantum of uh, tasks are uh, large quantum of downstream tasks with respect to the annotation. Uh, how do I say it? If, if we go to the other downstream, uh, I'm struggling for finding the right example. But yeah, you guys get. So, yeah, yeah, yeah. How and why this is difficult, and what is the labeling process, the videos, and all that stuff. I think so. He talked about in his video uh, the first section where all the images that are available, and these are the 4 points that he highlights to. Yep. So object category, other stuff. And so bounding boxes, image level, internet photos, real world, what's the complexity, what's the basic annotation. Uh, and in the real world, we come across some this hidden representations of objects too, with respect to if you look at it, many of the real world objects are occluded, and you have to get their proper annotation, and many times they are mislabeled. So that's one reason too. Uh, then in the medical 3D, that's one very good pertinent example. Now that we have looked at what's the requirement in the industry, we uh, go on. Plus, with the other sensory inputs with respect to, how do I say it, the audio, the GPS, and all that stuff, or a multimodal or a multi-objective based learning. You uh, 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 guys have an idea of what this is. It's with respect to the classification or the learning with respect to multiple uh, objects, multiple streams of data, and you can have a solution or with respect to powers or other stuff. I'm talking about the electrical grid or other stuff. So uh, along with multitask, this is also an optimization problem that I recently came across. This is one area that we can talk about too. Now, let's go to the problems of rare concepts. Here he describes the label of images that look like a long tail. And uh, here he describes the getting the annotated samples from categories towards the end of a tail that requires huge quantity of data to be labeled because of the nature of distribution of categories. Because in ImageNet, uh, this is the problem of low information and low classes of data that are there. Uh, so how do we solve that? And this is the frequency versus the rank. And the 10% of classes account for the 93% of data. That's an issue here. Yeah. These are the problems we defined. I would just like to give a shout out to I was in IClear. This was a presentation with respect with from Alexi, in which he talked about self supervision for learning from bottom up. And here he gave example of this because the labels are expensive, which I talked about, mechanical Turk and stuff. To get away from the semantic categories, get away from fixed data sets, to get away from fixed objectives. This is another way of looking at the problem in a nuanced way. Yeah. These this was the issues with the semantic categories, the chairs, the city, what labels like these are setting up the system to fail. The classical view of categories from the Plato and Aristotle, binary membership and stuff. the classical views of why humans do not do this. Typically, we have chicken, bird, bird, eagle, and sparrow. Uh, then we uh, then he talked about the bottom-up association instead of the top-down categorization, which have been uh, in the classical literature they have talked about in this and prototype theory and exemplar theory, uh, which asks what it is and what it is like. Yeah. So the uh, this guy. Um, so per exemplar distance, he gave a focus on the features and the feature two, and what can be the decision boundaries that are there with respect to the similar and the dissimilar side of things. Um, so this is an alternate representation. So I will just like to highlight some of the things that I think so. We will take a look at similar type of things in the next section of the uh, uh, talk. So I just wanted to go through a basic presentation of what his viewpoint is. And this is with respect to similarity learning and the contrastive objectives that we will take a look in PIRL and stuff. The data argumentation. This was a very good example, the choice of data argumentation and how it affects your uh, fine-tuned downstream task in which you're trying to gain uh, a critical confidence threshold on. So this was with respect to the poses too, which we will discuss. And the learning representation from a video. This also some of the tasks that we will take a look at from the slow features, the sparse coding, the contrastive learning objectives, the pretext, the distillation, and the auto encoder stuff, image in painting, and other things. This was space type correspondences for a contrastive random walk in which he tried to come up with a representation of the shoe here. So this is manually labeled, this shoe from this to this, and the supervised learning distance is this. And with the latent view, you can view it like this. So this is a shoe 2, this is a B. These are the representations. If you label it manually, how well the um, manifold connections look like with respect to the uh, data argumentation in the latent views, uh, how the self supervised learning will view it. If you go through the details of the paper that he wrote, you will get to know the exact reasoning of the structure of different layers. Uh, what is the query, the target, and the negatives that he talked about, and at each and every time steps. This is also a video, I think. The second was to get away from fixed data set in the real time motivation was the piece of data that first stressed then trained, and uh, repeating the same might not encourage generalization because it will be kind of like narrowed down to a particular data set. Then we can have that train validation pipeline in which we can online continual learning, like in recommenders and other stuff, like uh, Instagram and Twitter, and yeah, that they do with the continuous downstream tasks. Mm, this was with respect to the test time training with the generalization under the distribution shift. How can we manage that? The standard test error and the continual text error. How do we solve for this? The test and training. So yeah, this was a example with respect to the predictions and preventing the data drifts in the online version. And then this was self supervised in policy deployments in the reinforcement learning part. And yeah, and the third was to get away from the fixed objectives. Uh, uh, Fixed objectives here signifies the evolution with respect to how the arms kind of uh, trying to generalize based on the evolution, because objectives can be, as I alluded to here, the multi-objective optimization. This is the problem that he tries to evolve based on if in the future you have some kind of a new objective which or a particular objective that needs priority based on a certain evolution of the uh, common the policies from I don't know the policymakers in the government or something that they want your algorithm or your training to be or your inference to be a bit fine tuned. Uh, mm, so there we can have this kind of multi-objective optimization. And Amsati is this these self-play GANs and prediction as a meta objective uh, with respect to predicting the agent and complexity of the world and uh, how can we predict it further. So this was one work in GANs and in self-play too. The min-max objective that we have. And the self-play here is with respect to the evolutionary objective, which tries to come up with its own uh, best version in a closed environment after fighting its agent. So that's can be uh, symmetrical, or we can specify the final objective based on the certain conditions that we put up in our agent's code. And then he talked about the curiosity driven and other stuff. Uh, we will take a look at this in the RL section and the other stuff too that I initially alluded to. So yeah, and yeah, this was a quick uh, representation of why this whole thing is mm, mm, kind of makes sense, and there are uh, other viewpoints too. But let's now get to this. By Ishan. Uh, so I have talked about the different domains here. Uh, let's get back to what is self-supervised learning and what are the basics. He talks about the networks that follows supervised learning, where the labels are obtained in a semi-automated manner without human input. Here he also takes a look at the prediction problem, where the parts of the data is hidden and the rest is visible. Uh, uh, with uh, uh, the hidden data or some property from that hidden data, that's the feature space that we look at. Mm, yeah. Mm, Then how I supervised learning different from unsupervised or supervised. The unsupervised, it's kind of weakly defined, and supervised learning, yeah, it can be with labels and the feature space similarity, as we will take a look in uh, the parts. Yeah, let me do the slide as well here. Yeah, M, uh, M, plausible label, unsupervised, and the self-supervised from other modalities. We can, there are a lot of different viewpoints or trajectories that we can take a look, and we will discuss some of them in the upcoming sections. He then talks about word to vec and find this is the task that involve predicting missing word from that sentence, which is specifically omitted for the purpose of building a pretext task. So yeah, we can have this, and hence the if we view this, that's the word that is missing, and it is predicting the nearby word, WT, yeah, the projection layer. So, these are the embeddings. This is based on a softmax classifier. It's a classical method. So if anybody has any questions up until now, cool. So this is in respect to the NLP task. And let's now go ahead. Success of self-supervised learning in NLP. Powerful signals to learn representations. Yep, this he talks about the image movement, the ImageNet movement, the sentence word representations with birth, excluded the downstream tasks. I think so. In this bird paper, they had more than, exactly do not remember, but more than 10 downstream tasks that they performed well on. So uh, I may be wrong here, but then what is why self supervision helps in learning using the observations and interactions that require exhaustive annotations of concepts and leveraging multiple modalities or the structure in the domain. Uh, these were the 3 pointers that he discussed about in this part of the uh, uh, in this section. So yeah, now we go on to computer vision and what are the uh, contextual properties there. But and for NLP, I think we already have Kaggle tasks, and other uh, uh, channels too. And I think we also go through the paper reading sessions. So I don't think so. We should have a problem, but uh, please free to interrupt me anytime. Um, then we go on to the self-supervised learning in the computer vision with the pretext and a real downstream task. Here he defines about the pretext used for learning representation, sorry, which so there are 5 to 6 level of representations. I'm currently forgetting the hierarchy. It starts from the pixel to the end feature, notice, and yeah, right. Okay, I think so. You guys already know about this. We'll paste it in Slack afterwards. Uh, Then there are not the real tasks like the image classification that we care about. So this is we with respect to since we based on the we are in how do I say it pretext task with respect to mm, feature generalization, or we only currently here he only needs to talk about sorry he is talking about uh, visual representations which are learned in the model weights if we back propagate representations after a particular downstream task. That's the way we actually learn it. But here, it's kind of, how do I explain it? What's the difference between a pretest task? We can think about pretext task as a sort of a prior, like in Bayesian approaches, in which we have a generalized prior and we try to then tune it or fine tune it with respect to the downstream task that we are trying to solve. That that is presentation. So let me try to the spatial context. The paper that he talked about is this unsupervised visual representation learning by the context prediction, in which this is the work. Mm, This is a part visible and part hidden, while the task is to predict either the hidden state by the hidden data or some property of the hidden data. Okay. So here he talks about the patch base, the eight-way classification problem, uh, in which this is the uh, main part of the center part is the main randomly selected patch, and the rest are uh, fed into a classification algorithm with a eight-way and the eight-way. 8-way means here the possible locations of as you can see here, these are the patches that are above. It basically surrounds the current patch that was initially fed into the prediction with respect to the into the prediction algorithm, and what here is and what this algorithm is trying to do is predict the spatial arrangement. And why? Because uh, even I haven't gone through the full paper here, but what they try to do here is mm, so the general representations have been learned based on this guy here, this image, and the fine tuning, the downstream, is done on the basis of the patches, the input to we input the two image matches. One is the anchor, while the other is the query image match. So yep, as I have alluded to, so this is the input and these are the query. Uh, the input here x and the y here is three here. I think so represents the. I think so. This represents the position. Yeah, third location. Yep, this is the third patch that we talk about. And it tries to detect or predict uh, the relative position. So that's what this sentence gives overview of. Then this is the problem that can be modeled as an 8-way classification. So yep, he's talking about this stuff. And the label for the task can be automatically generated by feeding the relative positions of the query patch with respect to the anchors. So yeah, this is the relative position task. And how then we go on to how the visual representations are learned by the relative position prediction task. And yep, here we talk about the effectiveness by checking the nearest neighbors. Here we compute the CNN features, and then those features will uh, require an input patch or trying to predict uh, based on the downstream category that we want to. Uh, it can be on discriminator based GAN a GAN based approach, or any of the uh, approaches that we will take a look in the future sections. But yeah, uh, then those nearest neighbors are identified based on the vectors, the feature vectors of the required image from the pool that are available. This can be in three uh, positions. The three, sorry, uh, those matching clusters. The nearest neighbor, the query patch is the is shown here, and these are the matches from three different features: random initialization, the ImageNet Alex, which is based on the AlexNet. These three, uh, these were based on this paper's presentation, and what they try to detect here is the top group examples where algorithms perform well, as you can see, the, the random initializations, it's a bit the patches that are sampled here are too out of bounds. I mean the outliers are too great, so the prediction is not that uh, kind of cool. So uh, there you can see the representations which those patches. So, yeah. Hmm. So it's the similarity index which with the patch space which we go through. And why this is important, because if you take a look at the current state of the art approaches, like in swap or other argumentations, those argnex and other processes which are based on the patch based, how to hit those approaches in the self supervised uh, learning. So this was the initial, how do I say it, the uh, classical, I can say, classical uh, uh, research that was done in 2016, I think so. No, exactly. Yeah, 2016. And those methods that are used nowadays are an extension of this. So that's how we learn nowadays with respect to the network in a self-supervised settings. Please free to interrupt. I may ramble about this. Or, yeah. And then he goes on for prediction, predicting the rotation of images and why this is important. So there was this research, yeah, the rotations. This was presented in ICLEAR 2018. The predicting rotations is one of the most popular pretext tasks, which is simple and straightforward and requires minimal stamp sampling. And we apply rotations to 0, 90, 180, and 270 and uh, degrees here. And this can be uh, formulated as a four-way classification problem. And why this is important is this gives empirical advantage when you try to train. So, yep, these are some initial, as I said earlier, classical approaches for how do I say it, argumentations, which are useful nowadays. And he talks about this because intuition, uh, it needs to understand the rough boundaries and the representations in an image. So he talks about a tree that the roots will be in the ground, and the most of the green part that you can see is mostly above the ground, and that is if you view it from a top-down perspective, the sky will be at the top in the ground, and the sand will always be at the ground. Yeah, uh, that's how the uh, contextual information in image is learned. Yeah. Then, if we need to go in details, we can take a look at this too, the attention maps of how a supervised model So this is with respect to the saliency features. Uh, what it what it learns. Other stuff too. So when this is rotated, we look at the human face, the pup here, and the cat. Then we go on to colorization. This is uh, uh, why is this important? This is uh, a kind of prediction with respect to the colors in a grayscale image. Uh, this is not deterministic. It's why and because there are many possible solutions to a particular grayscale image, and how can that be colored? This is the work, I think so, yeah, color image colorization that he takes this image from. This is this, this are the projects that they work on. There was a recent, I think so, last year or last to last year, when Google Photos they announced this too, uh, to coloring the grayscale images. So if you try to upload your image into the servers, they will do it too. So these are the initial results, comparisons. As you can see when I hover my mouse on this, that's the example. You can see the interpretability, the deep stream visualizations, and so on. Plus, on the excellent digital post, there is also those interpretations, so you can spend a couple of hours there too if you want to go into the depth. This was a recent work in iClear, colorization transformers. This is same kind of work, but with respect to the transformers architecture, the decoders and the encoders and how they are trying to learn. So yeah, I will list all of these works in the uh, Slack after we have the call. So yeah, this is an alternative architecture for achieving the same downstream task. So let's move forward to fill in the blanks. Okay, so these are some representations which they have learned. As you can see, now let's go on to image in painting. Uh, this is with respect to the input context and what the human artist will fill here. Guys can see my screen. This is drawn by a human. This is the context encoder with the L2 loss and the L2 plus adversarial loss. So you can see the differences here with respect to fill in the blanks, image in painting, stuff. Random region, random lock, and central region. So, yep, there are other ways to do this too. Yeah.
Hey, Mayank, I got a
Mhm.
question.
Mhm.
How is adversarial loss formulated in this case?
Adversarial loss, I think so, is with respect to the min-max. Here, with respect to the GANs, the initial, the real and the fake, the generator and the discriminator features. So I think so. This is the initial representation that was used by Aeon. That was by Aeon. Aeon Goodfellow gave this uh, uh, formulation of the GAN, and I think so. This, with respect to the adversarial laws for the context encoders. Uh,
Okay, so I see. It's
mhm.
just like a GAN formulation, right? Okay.
Yes, this is
And
the initial. Here, M hat is the mask here. So that's the product between the M hat and the X. X is the input. I think so. That was with respect to taken. The image X, yeah, context, yeah, produces this. And this is the total joint loss that they gave here. The this one, L2 plus adversary. And this was the fill in the blanks. So now take a look at using videos. Uh, this is a bit tricky. Uh, uh, this is shuffle and learn. Uh, this is videos are composed of sequence of frames, and here the notion of the idea was some pretext tasks like predicting the order of frames and like filling in the blanks of some frames that were missing, or tracking an object or stuff. Uh, take a look at the presentation here, please. Uh, Based on the time series, what the sequence of data were, how to get self-supervision, predict the order of frames, predict fill in the blanks, track the objects and predict their positions. So this is a person that's on base role. What's the original video and what's the sequence of order that it produced? Given the start and the end, can this image lie in the middle? Of course, the formulation between for the shuffle and learn. That's what they have given in the figure 7, interpolation, and the figure 8, the shuffle and learn architecture here. So yeah, this input tuple is passed. This is a kind of a cross entropy loss that they use, and it's in the downstream it can be formulated as a binary classification problem if it's correct or not. So yeah, so this is what they are. So what it gives is if it is extracted in a right order, it's positive, or else if it is shuffled, it's negative. So if the middle is a valid interpolation of the two, as you might have seen in the magic tricks, uh, 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 the videos and the TV shows, or the how do I say it? Those coin magic tricks in which coin is present in one hand and then it's transferred to another position, or the magician tries to hide it or tries to replace it with something else. It's all too common now. Then he talks about the query ImageNet, shuffle and learn, and random stuff. Nearest neighbor representations. So here he talks about this is the triplet of the Siamese networks, and where the three frames. This is the internal architecture of it, how they are concatenated and given to binary classification to predict if the frame was shuffled or not. And then he talks about the nearest neighbor algorithm to visualize what's the network in the learning. And first we have a query frame, in which we feed forward to get a feature representation, and then look at the nearest neighbors in the representation space. So is this being affected? What is the query here? And the results that we get from ImageNet, the shuffle and learn, and the random. So here you can see the flow. So ImageNet will kind of give us the flow too. Here the shuffle and learn is trying to learn the pose here. So this is the pose. Uh, this is the pose that we get. And random, this pose is inverted. And here we look at the flow stuff. Here the query image is this grass. So we have this grass here, but this represents a pose here. And here it's inverse. Uh, While comparing, one can observe stark difference between neighborhood obtained from ImageNet, shuffle and learn, and others. So yeah, this observation that we discussed. This is a metric that we use here. So this is fine-tuned on the left. If you can see, this is fine-tuned on the human key point estimation. Yeah. This specifically works when we are trying to detect humans, because of course it will work because of the abundance of human data as compared to others in the data in the training examples. And here he gives an example of the ImageNet supervised in the shuffle and run. I think so. This paper was presented in 2016, and yeah, mm, and that was the state of the art then. So yeah, this as you can see the difference between supervised and the shuffle and learn. Uh, the difference here is just 1 point or something metrics. Supervised ImageNet and the self-supervised shuffle and learn on the like at this and they will put results on the key point estimation, yeah, as we have alluded to here. Then the pretext stands for video and sound. Here the odd one out networks. Here they refer to this network. So odd one out was not presented here. Let's take a look at it. Yes, yeah, just the odd one out network. Here, what they're trying to do is take several video sequences of to the input and get a network that shares reads. Objective is to add the odd video sequence. Uh, in this case, it is a video tool and find the odd video clip. Learning machines compare all the video clip, identify the regularities, and pick the one with irregularities. So this is kind of a network which correct order, the wrong order is predicted. Yeah, it's for video representation learning. Uh, what's the differences? The consecutive samples that it generates based on the video subsequence. And yeah, you can generate a deepfake based on it too to satisfy a particular, how do I say it, video representation, which is totally false. And this is the stack of different frames of video clip. Okay, then let's go ahead. Take a look at the pretext task for video and sound. Do you guys have any queries here? Okay, cool. That's the object that sound. This is from yours, DeepMind. And here, what they're trying to do is a multimodal, where sensory inputs for video and one for sound. Mm, yeah, this was published in 2018, in which The limitations for the previous cross-modal learning approaches with respect to teacher and student supervision. They proposed some novel, I think so, cross-modal references. Mhm. This is the audio-video correspondence, which is classified as a simple binary classification problem. Then the correspondences here show that this is the kind of a high-level architecture. The image, the video, and the audio sequence, and it goes through the coordinates. I think so. This uses the same principles as in wavenets. Uh, this is an example of how it's done. This is a GIF that shows the GIF representation, the visual localization network. This is from the latent space, and it tries to detect. If it's self-explanatory. Jump in if you have any queries. This is with respect to localizing, trying to detect in which part of image audio pairs, localization, and this is the contextual, how do I say it, the representation of the saliency maps, of which part of the frame the sound is being produced from, as you can see. This is with respect to the mismatch audio too. It's trying to detect this mismatch at the video samples. It's matching, it's being produced. So with you can detect voiceovers and such from this. So with respect to deepfakes, or you can use this to train your deepfake to be robust to that kind of uh, detections. So it can pass through uh, that security, or how do I say it, that uh, classification test in broad terms. So yeah, the probably many nefarious ways to use this. Let's now and then understanding what the pretext task learns. So this is all the questions and answers that he discussed in his talk. The rule of thumb, that stuff. If you guys have any queries, please feel free to jump in. Moving, I should go to the next section. That's oh,
Mayank, you there? I think we lost you. Okay, I think he lost his connection. I'll just message him on Slack, see if he'll be able to make it back. I have messaged him. We'll wait for like few minutes to see if he can. Yeah, he's back. Hi, man. Can you hear me?
yep. My
Okay.
computer got crashed. Hey, can you guys hear me now?
Yes.
Ah, uh, Sorry for the bit of a delay here, but let's try to finish this section as quickly as I can. Now, let's go on to scaling self-supervised learning. Here, what uh, Ishan is trying to tell us. Ah, Here we are trying to get the scaling with respect to the jigsaw puzzles. Jigsaw puzzles, as we have seen earlier, this permitted image patches. mm, Model with unshuffling the tiles back to the original configuration. Uh, we get back to the slides too. Uh, Here he talks about the Siamese networks for the jigsaw text task, and the tiles are passed through independently with encodings concatenated to predict a permutation. Uh, this is the permutation. Uh, Here he refers to the prediction by which the permutation is applied to the input, because you need to create a batch of tiles and that each tile of image is evaluated independently. Why we do this? Because in scaling the data and the self-supervised learning, these patches, as I've alluded to earlier, this is the crucial tenet of self-supervised learning. So here we explored across the three axes. Axes here represents to the pre-trained data, the model capacity, and the scaling of the problem complexity. We deal with these problems in the ML ops pipelines day to day, and it's a standard. How do I say it? Way to uh, learn and scale visual representations across uh, modalities and in the specific real world use cases. So let me try to quickly. uh, Yeah. So here, this is the pretext, the contrastive and the generative approaches here. This guy, in which you try to predict uh, jigsaw puzzles, self-supervised representation learning, classify which permutations, use 9 patches, and practice 9 factorial. Each patch is processed in independently and we coordinates. And the evaluation here, he talks about fine-tuning all the layers versus a linear classifier. So this is an example of transfer learning. Mm, So uh, when they evaluate this process across image classification with few shots learning, uh, across object and 3D understanding here, and the navigation perspective in the Gibson environment. And yeah, please free to jump in if I'm not making sense or uh, because I have to finish it as before in 10. So here, as we have seen, why this will help. This will help in the downstream task, as I've alluded to here. We uh, full advantage of the large scale of data. So it's the these are the ways to uh, extend it, as I've alluded to earlier, what the problems were. And they uh, tested out using the different methods with the, let's say, supervised, the jigsaw, image net sets, and they, in the various downstream tasks like image classification, and so low shot image classification in which only few shots pass through an image, then the visual navigation, object detection, the surface normal estimation here, the 3D understanding, and so these were the tasks that they tried their scaling approaches on.
I have a question.
Mhm.
So on here in the notes, it says fine tuning versus linear classifier.
Mhm.
Why does it say versus in the sense that you could do both, right? You could do fine tuning, which is start it as a initialization for the body, as FastAI refers to, and then still add a linear classifier on top and train the head, which is the linear classifier, a lot more, and then fine tune by kind of unfreezing, quote unquote, the network and training the rest of the network for a little. So why is it versus? I mean, you could do both. So in the paper, do they compare the two, or why is it versus? That you could do both, right? There's no reason why you should do only one or the other. And neither of them necessarily should take a lot of cycles, because to train the head on top of the body should be a few cycles, few epochs. And then again, to just fine tune the rest of the body, and while you keep, or it should also be less. So unless in the paper they compare or contrast, I kind of miss the versus usage.
Yeah, versus is here with respect to the distillation perspective. I think he refers to in his future this surface normal estimation and pretext, the general proxy task. I think we will take a look at this the next time around. But
Right. That's the distillation issue, I understand. But I'm talking about just, with the jigsaw task, if you then stick up a classifier, or you can fine tune, the
all the
entire,
layers. Yeah.
right. And it's either way, it'll take a small number of cycles, right? So maybe they're just comparing the two approaches of fine tuning, all like he has the picture, and in another case, just training the head and leaving the body untouched. Does he have another slide which shows just the head being trained, and that would be the linear classifier case, right?
I think
As
so.
far as I understood, the difference here, is not from perspective of getting best accuracy, but from perspective of how do you evaluate the quality of the effect of self-supervised, particular self-supervised task or self-supervised approach to the quality of extracted features. So in some way, one can argue that when you fine tune, so the final result depends also on kind of how much data you have and other stuff. And when you do only this linear classifier approach, but it might be like another way to understand how good are the features your network extracts from the data, right? So this versus, I guess it stands for there are two ways you can evaluate the quality of network trained in self-supervised manner. So you can view it as just as a feature extractor or as a backbone for future fine-tuning, right?
Yeah.
Yeah,
Plus,
Arto, but either way, you're evaluating it by, you're saying you're evaluating it on the downstream task, right? The quality of the learned representations, and using either of these two approaches is what you're saying, correct?
Yeah. I guess usually they do both approaches and report both results for both approaches. And in for example, in this recent Dino paper, they also do another approach for to evaluation. They do they just fit KNN classifier. So they do K nearest neighbor. Train K nearest neighbor classifier on top of the extracted features and measure the performance.
Yeah, in fact, even in this lecture, he talks about that's kind of what cluster fit is as we go through, because cluster fitting is clustering and then predicting the clusters, so which is kind of headed toward. But my question is, if we are doing that, then it also begs the question of, wouldn't you also want to compare where you would do both and say, is that better? Because why only do the versus? Meaning you're doing only the head in one case and only the body, or viewing it as initialization. But then I would say, why not combine the two and do that as well?
Yeah, well, I would guess that fine-tuning includes the fine-tuning head, right? So we just fine-tuning is just a broader approach, right?
Well, we can also think of it as a kind of pre layer that just has how do I say a kind of a evaluation, a kind of a routing layer in which that how do I say that linear classifier will only route your networks. Let me try to quickly draw. So think of it as, again,
Srinivas, the fine tuning also includes the linear classifier, right? Like Arto had said,
Yes,
it's not just the network.
Yes, it's the entire thing as they portray it, right? But again, comparing it to transfer learning, the thing typically that's done in transfer learning is the linear classifier is trained typically, and that's why, and I haven't read the paper, so it may just be that they do the comparisons for all of the three approaches. But in transfer learning, at least you train the linear classifier a lot more because you're kind of starting from scratch, and then you do the fine tuning of the whole thing. But the fine tuning is for a very few cycles of the whole network.
Yep. This classifier objective can also be thought of like a linear kind of uh, 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 networks to how do I say it, to reduce your computation across classification or of networks. There was a recent iClear paper that I had gone through. Maybe next time I will try to give a uh, uh, representation with respect to the diagram, the which I was trying to draw. My computer has again crashed, so I'm extremely sorry. But yeah, I have a viewpoint of why this is done, and when you're trying to actually scale it across different modalities or trying to save computations. So yeah. That was my viewpoint. I think so. We should end this call for today, and we might catch up next time, and we will resume through the next part of the theory, and then go through the practicum.
Sounds good. Thanks, Mike. Yeah,
Cool.
and at 10:30 we have, I mean, in half an hour we have the Kaggle meeting, which has a presentation on how to use weights and biases for one of the Kaggle competitions that we are doing right now. So if you're interested in that, make sure to attend that. Yep. Thanks everyone. Thanks for joining. Thanks, Mike.
Okay, cool. Thanks.
Thank you.
Take care.